how we would bias it with two DC power supplies, and then later we'll show you how we can bias it with one power supply using resistors, guys. NPN, this is the guy. So what I'm gonna do is, let's see, let me hook up the speakers and play a video for y'all. Let's see, I don't know. I guess I can control it here. Which one's volume? Okay. Looks like it's turned all the way up. You're right. I can go. I go to sleep in front of the TV sometimes. So y'all okay on these formulas right here? Or these should be on your formula sheet, right? Okay. We're under BJTs. I don't know. I don't have the formula sheet on the back. Just flip it over. And is it on the back? No, it's still on the front, right? Back. Yeah. So next class, I'll probably try to get this multi-sim working. But what we're going to assume, guys, so which is the highest current in the transistor circuit? The emitter current, followed by the collector, followed by the base, right? Okay. Now the problem is that in our calculations we're going to assume that IC and IE are equal each other, and why is that? Because well, yes, but the base current is almost nothing. So IE is IC plus IE, but so I'm sorry, IE is IC plus IB, but IB is almost what? Virtually nothing, right? Like a while ago, we said if we have a beta of 100, then we got emitter current is what, 101 milliamps, and collector current is 100 milliamps. So in math, if I use 101 milliamps or I use 100 milliamps, you're going to come up with, and everything's approximations anyway is close enough, right? So all practical purposes, guys, we're going to assume that IC in our math, we're going to assume that what IC and IE are equal. But if you see it on a test that says IC and IE are equal, you're going to say false, right? Because they're not. It's approximately. They're approximately equal. And that's what that little squiggly line means right there, right? Is equal, right? Why? Because they're so close. We already talked about this. We got three regions we can operate our transistor in. We can operate it in saturation. And when we get saturated, it acts like a what? A close switch. When we cut off, it acts like a what? Open switch. And we call this the active region. In the active region, it acts like a what? A rheostat that's electronically controlled. You're controlling it with what? With base current, right? The more base current you put into it, the resistance of the transistor goes down. The less base current you put in it, the resistance of the transistor goes up. But we're controlling it electronically, right? Y'all understand that? We're controlling it electronically, not manually like you would do a rheostat. So we have this thing called beta. So what we're looking for is beta is the ratio between IC and IB. And this is called beta. And we use the group symbol for beta in math equations. So beta is equal to IC over IB. So beta is in these transistors are always going to be greater than 1. And why is that? Why is that? Because IC is a lot bigger than IB, right? You understand? IB is the smallest current in here, right? Transistors operate in the active region. The collector current is proportional to the base current. The DC beta, called beta DC, is the current gain of the transistor and is the ratio of the DC collector current to the base current. You know, anytime we calculate gain, gain is always calculated without divided by N. And gains have no units. It's any gain. Power in over power out over power in would be power gain, right? But gain is out over in, because you know, yeah, or anything, and it has no unit. It's a multiplier, right? You understand? So if I said I had a beta of 100, what is that? That's no unit. It's just a beta of 100. It just means if I had a beta of 100 and I had 2 milliamps worth of base current, then I would multiply that by 100, and that would give me 200 milliamps worth of collector current. It is no gain. It's just a multiplier. It's just like if I was going to double your salary, you'd say, oh, good, you're going to give me a $2 an hour raise, right? But it's not. It's a multiplier, right? So when they give me a percent raise, they say, we're going to give you a 2% raise. They don't say a $2 raise, right? It's 2% of what you made. It don't have any units. The DC beta is the current gain. DC beta is a constant ratio called the current gain. And the problem is, guys, is that you're going to see beta all over books. In the books, that's what they call it. They call it beta. In the data sheets, they're going to call it H sub FE. So in the data sheets, when I want to see the beta, if you could look all day for beta in a data sheet and it's not going to be there, it's called H sub FE in the data sheet. And it stands for you don't need to know this, the hybrid forward transfer ratio with the emitter common. No, you just know I'm looking for H sub FE. On what? What's that? Yeah, this is beta DC. That's what we call it, but in the data sheets, it's called H sub FE. That's all I'm saying. So beta DC is beta DC. It's just for some reason, they don't call it beta in the data sheet. It's the same thing. What's that? Yeah. That's not B, that's beta. That's the Greek for beta. Yeah, beta, this is not the letter B. It's the Greek symbol for the word beta. It's just like this. Well, that's the Greek symbol for omega, but we call it what? Ohms, yeah. So beta DC is the same as H sub FE in the data sheet. So if you wanted to see what the gain of the transistor was, right, with the emitter common, which is what we've shown so far. So this right here, this is what we've been drawing so far. I've been making the what? I've been making the what? I've been making the emitter common. Huh? Yeah, every time I've drawn it. And this is usually what we do. So it means it don't mean it has to be connected to common. What we mean, it has to be pointing toward common, right? So when we start looking at this in the data sheets, we're going to be looking for what? H sub FE. Formulas, guys. So we can chart, we can solve. We've got beta, and that should be in there, right? And then now we can come over here and we can put it in our what? Put it in our triangle. So what would IB be equal to? Well, we would cover it up, right? You understand? So IB would be equal to what? IC over beta. Well, anything that's got three terms. Anything that's got three terms. Power, you can do power. You can use. You'd have to do square roots, but you can actually say, power is equal to I square R. Well, you could say, well, R would be equal to what? So we take that. Yeah. So that's what's the beauty of all our equations. All our equations are what? They're three term, right? So that means we can take any equation. Well, that's not true, but most of our basic equations are what? Yeah. Let me correct that. Our basic equations are three terms. I do too. And so, what would IC be equal to? Yeah, IB times beta. So all these should be in your formula sheet. Are they in there? So you can transpose them, but I think we've got all three of them. Yes. Now, alpha is the relationship between the emitter current and the collector current. And they don't give you alpha in the data sheets. But we can calculate alpha. If we know the beta, we can calculate the alpha using that formula right there. So alpha will always be less than 1. Y'all understand why, right? Because you're saying beta over beta plus 1. So that means the bottom number will always be greater than the top number. So alpha will always be less. It's usually 90s. It's usually in the 90s. And we'll see where that comes into play. So DC alpha is actual IC over IE. So all these formulas in the formula sheet. This one's in there. So what do you think that means? Yeah, on this test, right? That's a good one. That was right. Okay, guys, this is important to know, is that we're going to make measurements. We're going to calculate voltages. And guess what laws we're going to use to calculate voltages in a transistor amplifier? Well, that would be power. Ohm's law. So all we need to know is Ohm's law. So you already know almost all the formulas you need to calculate these amplifier circuits. But when we start calculating stuff, we're going to calculate voltages, and they're going to be relative to common. So if I was to come over here and draw this circuit right here, this is actually an amplifier called a common emitter amplifier, and it is the predominant amplifier, guys. and we would take our output right here, and we'd take what we want to input right here, and we're going to have to add something a little more to it. So generically, I'm going to call this R1, and I'm going to call this R2, and we'll call this RC because it's a collector resistor, and we'll call this RE because it's the emitter resistor. Now, let's say this right here was 33K, and this down here was 5K, and I put 12 volts right there. What would that voltage be right there? This voltage right here we would call VB, because when I measure it, I would measure it from common to that guy right there, and that's going to be what we call our base voltage. So what would VB be equal to? You already know how to calculate that. It's a series circuit, guys. We're calculating the voltage drop across the 5K. That's what we're doing. So what would the voltage drop across the series circuit? Gave you two resistors, gave you the size of the two resistors. Oh, I'm sorry. It did 12 volts. I just run it together. Yeah. Y'all don't know how hard it is to draw on something that bounces when you're drawing on. So that's my excuse anyway. Yeah, but it bounces. Y'all see me try to hold it. So what would be the voltage? And guys, you are calculating an amplifier. And I'll show you. It's really, really neat. So what would be the voltage drop across the 5K? Where did y'all learn to do this at? DC. That's all we're trying to do is calculate the voltage drop across that, and that would be VB. Woo, that's good. See how we got that? Pretty simple. All right. Now my emitter is pointing toward common. I have 1.6 volts there. How much is this guy going to drop? His forward bias. How much is it going to drop? It's going to drop about 0.7 volts. That means across this resistor right here, I should have around 900 millivolts. Is that right? Now let's say RE is, let's say it's 1K ohm. Then what would be the current flow through? I know the voltage, I know the ohms. So now what we're going to do is we're going to calculate IE. So what would because the current flow through RE is going to be IE, right? You understand that? So what would be the current flow through IE? It's going to be what's his voltage drop? 900 milli. What's the size of the resistor? 1K. I wrote it in here. Sorry. Yeah, the volts was given. V over R. So let me do it. Divided by 1. That's milli. $900 million. And then we move it over 3 places. You know you can't argue with that man right there. So let's say this guy up here is a 6.6 k ohm. Well, we already know the amperage. We calculated IE. So I've calculated IE. Y'all pay attention. Y'all doing some, and what we're doing is we're taking Ohm's law and we're applying it to a circuit that we can get a gain out of. If this is not a passive circuit, this is an active circuit. So here comes IE right here. Where does it go? Well, about 1% goes that way, so we're going to ignore it. We're going to look at this guy right here. We're going to calculate this like it's a series circuit, because IE and IC are so close together, and all our resistors have all this tolerance, right? You understand that when we calculate this, we're just going to ignore I. We know it's there, but we're going to be able to do what? Ignore it. So how much voltage will that guy right there drop? So V is equal to what? Ohm's law. I, 900 micro, times R is 6.6 K. So VRC, I should have did it. Yeah, we calculated 900 micro right there, Bernard. See that? Yeah, I just couldn't make it big enough. Let me move this up here. It's 900 micro times 6.6 K. So where'd y'all learn this at? DC. So how much what would VRC be? What's that? 5.9 volts. Which is okay. That's where we want the amplifier to operate. We would like for a good amplifier, we would like this voltage right here to be 1/2 of that voltage right there. And we did really well. So what would my collector voltage be? Well, VC, where are we going to measure VC at? And this is where people mess up, guys. I'm going to measure VC right here. So what would VC measure? VC, collector voltage. So these voltages are all reference. I should mark out ground, guys. I should put what? Common, circuit common. Because every circuit is not connected to ground. So what would VC measure? No, that's the voltage drop on this resistor right there. That's how much that resistor drops. Yeah, there you go. Should measure what? 6.1. Well, what happened, that's a common mistake people make. They want to use the voltage drop across that resistor for VC, but that's the voltage drop across that resistor. What would the voltage collector to emitter be? Got 6.1 volts right here, got 900 millivolts right there. What would it measure right there? Everybody agree with that? So how do you do that, Brian? 6.1 minus 900 milli. That's exactly right. What are these laws? This is Kirchhoff's voltage law, right? So, yeah, I understand that. So what we're doing with this guy, guys, is we're treating it like this. We're treating it like two series circuits. Everybody understand? This is the way we calculate. We calculate it like two series circuits, and then we're off the same power supply, and we're calculating it like this. The problem is that the transistor is acting like one of these guys right there. But I don't know the resistance of the transistor. And the way we calculate this voltage right here is whatever voltage you calculate there, you do what? We take VB, so VB minus 0.7 for silicon, and that gives us that voltage. If we know that voltage and we know the size of the resistor, then we can calculate what? Then we can calculate IE, and we assume IE and IC are equal to each other, right? You'll understand why we can do that. They're so close that it would be, we could probably measure it with our meters, because we're going to be in the milliamp range, so our meters will probably measure it, but it's only going to be like 1 or 2 milliamps difference between IE and IC, right? Well, we're not even calculating that. We're not even technically calculating IC if we measured it, if we were measuring it. We're going to ignore it when we calculate, and why is that? Why can we ignore it? Is this going to be exactly 1.6 volts? Why? Because that power supply might not be exactly 12 volts, that resistor is not going to be exactly 33K, and that bottom resistor is not going to be exactly 5K. Yeah, so that's what I'm saying. If we ignore the base current, the base current flowing through the emitter, when we calculate the collector current, it's going to be well within the limit of all our resistors, right? Does that make sense? But there's got to be base current. What does that mean, guys? Yeah, I'm good. So what's the plan for Tuesday? It's up to you whether you want to take tests. If you don't take it, I'll give you what you made on the first one, not the second one, because that was cheating on that. Go ahead. Yeah, we'll definitely have worksheets on this. Definitely. Yeah, worksheets are always better. By the way, the circuits on Monday's test are going to be similar, but they're not going to be the same. Y'all seen these exact circuits 3 times. Y'all taking notes on them, right? You understand. They will not be, they'll be close, but they won't be the same. So the math will be the same, but the circuits won't be. Y'all understand why, right? Yeah, by this time, y'all almost got these answers memorized. And this is going to be the last shot at this test, right?